Welcome back, everyone. Today we're diving into a seriously fascinating explainer. Have you ever stopped to wonder how we actually get pure gasoline from thick, dark crude oil? Or how perfumers extract the exact essential oils they need to make something smell incredible? Well, it all comes down to a fundamental process called distillation. We've got a highly structured visual breakdown of industrial distillation for you today, based straight on the excellent foundational notes from Professor Lucrecio Fabio de Santos of the Chemical Engineering Department. We're going to break down those massive industrial towers you see from the highway and figure out exactly what's going on inside them step by step. But first, I want to pose a seemingly impossible question. How on earth do we separate liquids that are perfectly mixed together? Think about it. If you mix sand and water, it's easy, right? You just use a filter. But what if you mix two liquids that blend seamlessly into a single, uniform solution? You can't filter them. You can't just scoop one out. Solving this core problem is exactly what chemical engineering achieves, through what we call unit operations. And distillation? Well, it's arguably the king of them all.
So here's our visual roadmap for today. We'll start with the separation challenge, move on to large-scale industrial applications, dive into the science of volatility, explore liquid-vapor equilibrium, and finally wrap up with the process in practice.
All right, let's jump right into Section 1, the separation challenge.
At its core, distillation is a unit operation specifically designed to separate homogeneous mixtures. We use it primarily for two things: separating perfectly mixed or miscible liquids that have different volatilities, or separating liquids from solids that have completely dissolved right into them. The crucial point here is that the mixture is homogeneous. To the naked eye, it literally looks like one single substance. So we have to use the fundamental physical properties of the chemicals themselves to pull them apart, specifically by partially vaporizing them.
Moving on to Section 2, large-scale industrial applications.
Take a look at this magnificent piece of engineering. When you drive past a chemical plant or a refinery, these towering distillation columns completely dominate the skyline. The sheer scale of this equipment is breathtaking. Inside this massive steel cylinder, there's a continuous, colossal cycle of boiling and condensing happening. It's this exact equipment that makes so many of the everyday products we rely on even possible. And what exactly are they cooking up in those massive towers? The range is honestly incredible. In petroleum refineries, distillation separates raw crude oil into lighter hydrocarbons like gasoline, diesel, and jet fuel. In the biofuel industry, it purifies ethanol. They even use it to separate the very air we breathe. They literally cool it down until it's a liquid, then distill it to get pure oxygen and nitrogen. Throw in the manufacturing of distilled spirits, extracting essential oils for perfumes, and even desalinating seawater to create fresh drinking water. Distillation is truly everywhere.
Which brings us to Section 3, the science of volatility.
Okay, let's get into the science making all this happen. The absolute cornerstone of distillation is a concept called volatility. Put simply, volatility is just the tendency of a substance to vaporize or turn into a gas. Every single chemical compound has its own unique eagerness to escape from a liquid state into a vapor state when you heat it up. For instance, alcohol evaporates way faster than water at room temperature because it's more volatile. Distillation completely hinges on this simple fact. Because different substances have different volatilities, they will react differently when we apply heat to the mixture.
Let's visualize that. Here we have a simple model of a closed container. We've got liquid at the bottom labeled L and vapor at the top labeled V. Those arrows show molecules moving between the two phases. Now let's say we have a mixture, and component A is the most volatile one. The X represents the concentration of component A in the liquid, and the Y represents its concentration in the vapor. If you look at the math on the right there, YA is greater than XA. Because component A is more volatile, it escapes into the vapor phase much more eagerly than everything else.
So here is the massive takeaway. The generated vapors will always be richer in the more volatile components than the initial liquid mixture was. If you have a liquid mixture that's 10% alcohol and 90% water, the vapor that boils off isn't going to be 10% alcohol. It might be 40% or 50% alcohol, simply because the alcohol is so much more volatile and escapes faster. This unequal, disproportionate distribution between the liquid and vapor phases is the exact scientific engine that lets us separate the fractions.
Now for Section 4, liquid-vapor equilibrium. Let's look at this phase diagram of a binary mixture, meaning a mixture of just two components. I know graphs can sometimes look a bit intimidating, but this brilliantly illustrates the whole process. The vertical axis is temperature. Down at the bottom, in the cooler zone, everything is a subcooled liquid. Up at the top, in the superheated vapor zone, everything is a gas. But check out that space right in the middle, between the red and blue curves. That is where the magic happens. That's the zone where liquid and vapor exist together in perfect equilibrium. As we heat a liquid mixture up from the bottom, we eventually hit that red line. That red line is known as the bubble point. Let's demystify the jargon here. The bubble point is exactly what it sounds like. It's the precise temperature, at a specific pressure, where the very first bubble of vapor is born from the heated liquid mixture. It's the exact moment boiling officially begins. And from that moment on, as we keep adding heat, more and more vapor is created. And as we just learned, that vapor is packed with our highly volatile components.
And that creates a really beautiful, natural sorting mechanism. We can contrast the two phases here. Because of the heat, the heavy, less volatile components remain trapped down below as a liquid. Meanwhile, the lighter, highly volatile components eagerly escape upward into the vapor phase. In those giant industrial towers we saw earlier, the separation is happening constantly across dozens of different levels, perfectly sorting heavy molecules toward the bottom and light molecules toward the top.
Finally, Section 5, the process in practice.
Check out this classic laboratory setup for differential distillation. If you took high school chemistry, this probably brings back some memories. We've got a round boiling flask on the left, sitting over a burner, a thermometer at the top, a downward sloping tube called a condenser that has cooling water running around it, and a collection flask on the right. What's so amazing is that this simple benchtop glass apparatus mirrors the exact fundamental steps happening inside those massive multi-million-dollar industrial towers. The principles are literally identical.
Let's trace the steps logically. Step 1. The homogeneous liquid mixture in the main flask gets heated by the burner. Step 2. As we hit that bubble point, the most volatile components vaporize first and rise up as a gas. Step 3. This gas travels down into the condenser, where cold water running along the outside cools the vapor right back down. Step 4. This cooled vapor condenses back into a liquid, drips down, and is collected in a totally separate flask. We have literally pulled the liquid apart using heat.
And that brings us to our final result. We finished the process with two distinct liquid fractions that now have completely different chemical compositions based on their volatility. You have the residue left behind in the original heating flask. This is a liquid highly concentrated with the heavier, less volatile components that just couldn't easily boil off. And over in the collection flask, you have the condensate, a newly formed liquid highly concentrated with the lighter, more volatile components.
It truly is an elegant solution to a really complex problem. So I want to leave you with this thought. The next time you fuel up your car with gasoline, or spray on your favorite perfume, or even just enjoy a glass of clean water, ask yourself, how many distillation cycles did this product have to go through to get to me? Once you start looking at the world through the lens of chemical engineering, you gain a whole new appreciation for the incredible, unseen operations making modern life possible. Thanks for joining me for this explainer, and keep asking questions.